Let's look at the next concept in probability called conditional probability. In practice, a lot of events are connected with each other, and they can impact the probability of each other. When the probability of events are influenced by another event, it's called conditional probability. These events are called dependent events, so they're no longer independent. We're saying something happened because of something else. Let's consider examining admissions records for a university based on gender. This table consists of two events, admissions A and gender B. Each cell is the intersection of the two events. So we create this table where we had 625 men admitted and 215 men not admitted, 710 women admitted, 184 not admitted. The totals could go straight across. There were 840 men, 894 women, and then vertically we can count them as well by adding them, and we have 1,335 admitted, 399 not admitted, with a total of 1,734 applicants. The joint probability is done by dividing each cell by the total, and it gives us the probability of both events occurring. This is known as the joint probability. It is the intersection of the two events, the probability of A intersect B. So here we have men and admitted is 625 divided by the total, or 1734. By doing that division, we get a percentage or decimal number of 0.3604, or 36%. We do the same thing for each one of them, and we would get the joint probability for any one of the cells. As we said, the joint probability for a person being admitted and being male is 36%. The joint probability for being admitted and the person being a female is 40%, or close to 41%, 0.4094. But notice that when we do this, all of the probabilities still add up to 1. The next concept is the marginal probability. The probabilities in the total columns, whether it's horizontal or vertical, are known as the marginal probabilities because they occur in the margins. So the marginal probability is interpreted as the single event probability. So in the case above, the applicants being male is 48%. Applicants being female is 51%. Now, the conditional probability is read as the probability of the event occurring given the fact that the other event has already occurred. In the example below, the goal is to find the probability that a student is male given the fact that the student was admitted. This is written as the probability of male, a vertical bar, and admitted, and we read this as the probability of male given the fact that the person or the student was admitted. And the formula is actually pretty simple. It is the probability of A and B over the probability of B. Now, some students get a little bit confused as to what goes where. So to simplify it, the numerator is nothing more than the and of both of those events, A and B. And the denominator is simply going to be the one on the right-hand side, which in this case is B. So using the example, as we said, the conditional probability is read as the probability of an event occurring given the fact that another has occurred. We're trying to find the probability that the student is a male given the fact that the student was admitted. So we would write it this way. The probability of male, given the fact that they were admitted, is the probability of male and admitted divided by the probability of admitted. And therefore, all we have to do is now look at our table to figure out what the numbers are. Computing the probability for the formula, we look at the intersection of the probability of male and admitted, which we've highlighted here in red. And that's 0.3604. And we look at the probability of just being admitted in general, and that's 0.7698. We take the first number divided by the second number, and we get 0.4681. So the probability of male, given the fact that the person is admitted, is 0.4681. The notation for this, and looking, is again probability of A given B, which is the probability of A intersect B divided by the probability of B. On the Venn diagram, this is represented below, where the intersection of the two sets, A and B, is represented by the blue region, and it's divided by the red region itself. The conditional probability equation has as its numerator the joint probability of the two events. Recall that when looking for the probability of two independent events, the product of the probabilities is performed. But when the events are not independent, that is, it's conditional, the multiplication of the intersections is given by the following. But using a bit of algebra, we can actually rewrite this, and we can say that the probability of A given B times the probability of B is equal to the probability of A intersect B. So therefore, the intersection of A and B is obtained by the probability of A given B times the probability of B. Okay, so completely confused. I thought the multiplication rule said to just multiply the two probabilities, and now we get this formula? Well, let's take a look at the formula a little closer. We have our probability A given B times the probability of B, and this we said is the intersection of A and B. So if the probability of A is related to the probability of B, then the probability of A over B will be a value between 0 and 1. But if the events are independent, then the probability of A is not dependent on B, and therefore the probability of A given B is really just the probability of A, nothing else. And in the case where A and B are independent, the formula simply becomes probability of A times probability of B, which is equal to the probability of A intersect B. So they are the same formula. It's just a question of whether or not they're independent or not, that left part is going to change a little bit.